Welcome everyone. I'll begin. So my name is David Howie. I'm an associate professor at University of Oxford in the Engineering Science Department. It's great to have you here, and I'm very grateful for being invited to help facilitate this session. What I'm going to do is speak for just 5 or 10 minutes to introduce the topic of digitalization and battery control. And then we'll take 25 minutes to have some Q&A using the Menti platform, and Pablo is kindly going to help us with that. If you want to ask a question, please feel free. Maybe the easiest way to do that is to just type a message in the chat on Zoom, and then I'll pick those up once I've finished my presentation. Okay. So if you want to get in touch with me, this is my email address. This is my research group. I'm based at Oxford University, and we have a group of about 10 people interested in modeling and control of batteries. And just to introduce the topic today of battery control, I'm sure that many of us in this breakout room already are familiar with this topic. But just in case you're not, this is how I kind of see things. So within an application such as an electric vehicle or a grid storage system, you will have different layers of sensing and estimation and control. At the inner level, there will be some direct monitoring of voltage, current, and temperature, and some direct safety circuits, passive and active. So this might include overvoltage, undervoltage, fuses, that kind of thing. So the first and most important priority with a battery management system is to protect the safety of the system and of the occupants and the users. And then as we move out from that, there are other important things as well. So the next layer is this kind of green layer where it says indirect monitoring. And that's where we estimate things like state of charge and state of health. And then finally, we get to make some decisions. So in these kind of systems, there will be a user interface, there will be some control, thermal management, etc. And so how can battery control make a difference? There's a list of different things here, but in a variety of ways: state of charge estimation, state of health, power capability, lifetime prediction, balancing of cells, thermal management, charging. And then in a grid application, you might have full control over charge and discharge, for example, for energy arbitrage. So I just want to pick off 3 of these things in this list to give you some quick examples of our own work in these areas. And this is really just as a starter for discussions and thoughts. I'm sure many of you have other examples as well. So the first example is temperature estimation, and I think this was already mentioned earlier in the workshop by a few other people. So we can use the battery impedance actually as a temperature sensor, and in the past we've done some work to combine impedance, which gives you a kind of a volume average temperature measurement. We combine that with a thermal model, and we've demonstrated that this is quite an accurate way of getting hotspot temperature estimates. So what we're looking at here is on the left, you can see some simulations using a thermal model of a cylindrical cell. These temperature sensors T1, 2, 3, and 4 are different locations. So T1 is in the middle of the cell, and then 2, 3, and 4 are on the surface. And these graphs here show a comparison between temperature directly measured, which is the black lines, with temperature estimated using impedance combined with a low order thermal model. And this down here shows the actual decrease in the impedance as the cell warms up during a discharge. So this is quite a high rate discharge, a 6C discharge. And if you look at the comparison of the errors, you get within about 1 or 2 degrees C RMS error. So temperature estimation is one area of interest. The next area of interest is something that we are currently doing a lot of work in my group on, and this is trying to estimate battery life and predict failure from field data. So this graph here shows about 1.5 years of voltage measurements, actually from a lead acid system, but the principle applies equally well to lithium ion. And we've developed some systems where we try to estimate the state of health of this battery from the live data. And in this case, we actually use the internal resistance as a health estimate. But the problem with internal resistance, so that's R0 here, is that it's of course a function of state of charge, current, temperature, and time. So we have to somehow map all of those things directly from the data. And so what we've developed is some machine learning techniques combined with simple circuit model, which allows us to estimate these curves, if you like, this kind of 4-dimensional surface. So you can see as we see more and more data, we track through time, we can see that these curves kind of change shape. The system kind of learns the behavior. Now, the important thing about this is we can then use, for example, the resistance calibrated at a given state of charge, current, temperature, just as a function of time to indicate some kind of fault. So in a simple case, for example, we choose a fault threshold. And we're currently doing work to compare these metrics with data from the database of the company that we're working with for when units were sent for repair. And we can predict fairly accurately with about 85% accuracy when a system is going to fail and be sent for repair. So the third area that I just want to highlight is grid energy storage for arbitrage. And we've done some work recently in collaboration with Energyville and Vito on using the single particle model, which, if you're not familiar with it, is a simplification of the Newman P to D model within an optimization algorithm to do energy arbitrage. So we take some price information. This flowchart kind of shows the comparison of what's going on. So we take some price information, which in this flowchart is not actually shown directly. And then we combine it. Oh, sorry, the price information is buried in this tiny picture here. We combine the price information with two different modeling approaches as a comparison. So the conventional approach is to assume the battery is just like a bucket for energy and maybe apply a simple linear degradation function so the battery would degrade as a function of cycles, for example. So this approach is often used, for example, by economists. We then solve an optimization problem, which decides how to charge and discharge the battery. But the approach we looked at was to use this more sophisticated physics model. And that then becomes a nonlinear optimization problem. But we then took the optimal profiles that were generated from this algorithm, and we put them through a battery on a test bench for a year. And these are the results shown here on the right. So this plots revenue, or what would have been revenue from charging and discharging for energy arbitrage versus lost capacity. So what's interesting here is that going to the physics-based model, which is the yellow curve, actually we end up with a different gradient. So in other words, we can generate more revenue or more profit really for less degradation. So there isn't so much of a trade-off between revenue and cycles. For example, we actually go onto a different curve. So I think that's quite exciting because this shows that these physics-based models really have some promise for control. But there's still lots of challenges, and that's my final slide. So I think I'd like to hear from you today what you think the challenges are, but these are some of the ideas that I had. So a big challenge, especially with physics-based models, is parameterizing the model. Most physics-based models have a lot of different parameters, and making sure you get a consistent parameter set is tricky. I think another big challenge is that a lot of what we've demonstrated in academic labs is just on a cell level, where actually to be useful, this stuff has to work on a module or on a pack level. So bridging that gap is important. And that's going to require us to think about cell-to-cell variability. So here's a simulation of 10,000 cycles for a pack of 2,700 cells. And you can see that there is significant cell-to-cell variability by the end. And then finally, especially for real world estimation of health, validation is a really big challenge. Often we don't have controlled charge-discharge cycles. So it's very difficult to know whether your estimator is actually correct or not. Okay, so those were the only slides I wanted to share. If you want to contact me after this, please send me an email. This is my email address, just david.howie@eng.ox.ac.uk. What I'm going to do now is stop sharing my screen and hand back to Pablo to share his screen, because we're going to switch into 20-25 minutes of discussion to hear your thoughts on this topic. But while we get that set up, if anyone has any questions on what I presented, feel free to put a message in the chat and we can try and unmute you if you want to ask the question directly. Great. So we've got a question from Michelle. I have a question. When you talked about internal resistance for state of health estimation of lead acid, what exactly do you mean by that? Impedance at a specific frequency, voltage drop of constant load? Yeah, that's a very good question, Michelle. I think that what we mean by that is dependent on the measurement system. And in this case, the measurement system, I think it was measuring internally at 1 hertz, or it might even been slower than that, maybe even 1 minute. So I think the resistance that we're measuring is actually a combination of ohmic and charge transfer and maybe some diffusional effects. But we sort of throw away a lot of that complexity and use a very simple circuit model. And then instead of having the complexity in the circuit, we put the complexity back into kind of machine learning approach to learn the resistance directly as a function of current, etc. And what we see kind of looks like a Butler-Volmer type relationship. It's doing the right things. It doesn't do exactly what you expect, but it's enough for us to actually come up with an accurate state of health indicator that we can use to predict failure. I hope that answers the question. Pablo, do you want to, which algorithms do you use? Yeah, I can send you a paper on this. We use a lot of Bayesian non-parametric models in my group. Specifically, we use Gaussian processes for this. But the challenge with Gaussian processes is that they don't scale very well with the number of data points you have. So we've had to use some quite interesting techniques to overcome that challenge.
Sorry,
Pablo.
David, now I can share my screen, start
Please,
with the Mentimeter, and then if we have time, you can answer more questions if you want.
That would be great.
So, okay, can you see my screen right now?
Yeah.
Yeah.
Do you want to explain what we're going to do?
Yes, you can now, as we made in the active rake, you can access to this new code in the Mentimeter. And David, you can read the question if you want, and then all the attendants can answer, and you can make all the comments you want in the answers we received. So I will wait for 30 seconds for the people to log in. Now I think we have more or less 3 or 4 people in. So now 7. Okay, I think we can start. So David, now the floor is yours.
Okay, great, thanks. Okay, so the first discussion point, we have about 5 of these discussion points, by the way, and this is really just a way for us to stimulate some thoughts. So the first question that I want to ask you is, what do you think the pain points or bottlenecks are in this topic of battery control? And I've put down a list of things that maybe I think are important. So hardware limitations, lack of good data, parameterization, etc. But I'd love to hear what you think. And if you tick the others box, that's fine. I would love to hear what you would have put instead, in which case maybe you could put that in the chat if you just type it in. We'll just wait for 30 seconds or so. If you are wondering what's going on, head over to menti.com and use the code shown on the top of the screen to log in.
Yeah, David, I think almost everybody answers, so you can comment the results.
Yeah, okay, great. I'm just trying to make some notes as we go as well. So it looks like quite a few of us think that parameterization is a big deal. I would definitely agree with that. And I guess just to comment on that a little bit, one of the issues is that even with something like a circuit model, you start to run into issues at extremes of temperature and state of charge, and also you need those parameters to adapt as the battery ages. So I think coming up with concise experiments that give you good parameterization is still a tricky issue. But people have also ticked validation difficulty and lack of good data. So lack of good data, I completely agree with that. In fact, I'm in discussions with quite a few groups around the world to try and bring everything together so we can have more of an open and shared approach. And it was great to hear from Simon Clark and others earlier about what's happening in your EU projects. And yeah, I think there's a real opportunity here for us to work together in the way that the pharmaceutical industry, for example, has to try and share data. Validation difficulty, yeah, I agree with that as well. I think that this is a huge problem, especially in quite conservative industries like automotive, where convincing people that something more complicated is going to give you a benefit is difficult, especially if it's the profit margins are already quite narrow. So yeah, and then maybe on the flip side, it looks like some of the things like hardware limitations, software complexity, etc., are maybe less of a big deal, but still there in the background. I'm seeing some comments from people, which is great. Michelle says, others, he's ticked others, lack of good sensing data from individual cells, temperature, voltage, and current maybe is not enough. Yeah, that's definitely true, and that plays into the validation piece as well. Okay, should we go to the next question then? Yeah. Pablo, do you know what time we have to rejoin everyone? I know we're running slightly late.
I think we have 15 minutes right now.
Okay, so about 15:15.
Okay, yeah, we are on time. Don't worry about that.
Great. Okay, so the second question is, what are the main expectations regarding digitalization in battery control? So I guess this is more looking to the future. Where do we think these kinds of techniques would provide a benefit? So model characterization, fast charging, grid storage optimization, lifetime prediction, and extension. So adapting control systems as the cells age and maybe into second life, for example. Balancing systems, for example, using a lot of DC-DC converters to manage modules separately or whatever. Improving performance and safety range, or others. And again, if you tick others, it'd be great to hear what you've said in the chat. Okay, so it looks like a reasonably even spread between lifetime prediction and extension, fast charging, and then perhaps improving performance and safety range. Lifetime is taking a bit more of a lead. Yeah, this is an interesting topic. So we've just been working on a perspective paper on this, and I think one of the challenges with lifetime extension is that, again, a lot of industries, so automotive, for example, is quite conservative. They are required to fully validate everything in the lab before it goes anywhere near a car. And so demonstrating that you can actually extend life, that lifetime prediction has some value, I think is still not always, in my experience, is not always fully sort of accepted by people in industry. And it'd be great to hear your thoughts on this. I remember being in a meeting a few years ago with someone from a car OEM, and I said, oh, we can use machine learning to predict lifetime. And they said, well, why would we want to do that? You know, we already know what the cell lifetime is from the kind of the lab tests. So yeah, I think there's a case to be made for this, but I think we still have to convince other people of the value. So maybe doing some long-term experiments, you know, 3, 4, 5 year long, multiple cells in the field, showing people that this can really make a difference would be great. Comment on fast charging. This is obviously a very popular topic, and lots of literature on fast charging. I would say that I think some of the test conditions that we see in the literature seem to me quite unrealistic, you know, cells dying in 30 days or whatever. And I just, whilst I think the tools and techniques are interesting, I just wonder whether that's transferable to the real world. Certainly, I have an electric car. The fastest we can charge is 2C, and we don't do that every day. We do that maybe a few times a month. So I wonder whether we're actually underestimating battery performance. Okay, as I say, if you ticked others or you have any comments, please put a message in the chat. Shall we move to the next topic? Okay, what are you doing to reach your goals using a digital approach in battery control? So I guess this is more heading towards those who have a commercial interest in this area, but are you outsourcing your requirements here? Are you recruiting specialists, control experts, machine learning experts? Are you partnering with companies who have specialism in this area? Are you training people, or what are you doing? Looks like quite a range, but in-house department and in-house training seem to be coming out as leading topics at the moment. So I guess this will be a function of what kind of people we have in the room. Some of you will work for large companies, automotive OEMs, tier one suppliers, etc. Others might work for smaller startup companies, etc. One thing I certainly think I've noticed just in my own research group and the career destinations of my PhD students is that there's a huge need for people with experience in these areas. So I think it's a great topic to be working on, and to be helping to train people in this topic is really satisfying. Okay, I think unless anyone has others, basic research PhD, says Michelle. Yeah, I think PhD is obviously not for everyone, but I think the opportunity to do in-depth research on these topics can be great fun, and is a great way to get trained up on these topics. Okay, shall we move to the next question then, please, Pablo? So these are two questions, this one and the one after, are two questions that I thought might be interesting to get your views on. So the first, these are more technical questions, I guess. So the first question is, should we apply battery control and estimation models at the pack level, which might be like the container level if it's a grid storage system, or at the module level, so a collection of cells in a rack, for example, or at the individual cell level or parallel cell block level, I guess. What do you think? So this is a topic, this is interesting that cells coming out, or I guess we could take that as parallel cell block or cell brick. This is a topic that I have different views on depending on how I feel. So to me, one way of thinking about this topic is to think about what kind of sensors you typically have in the system and what kind of electrical arrangements the system has. And specifically, the number of current sensors and the location of the current sensors is very important, because that is the thing that underpins state of charge estimation. So my view on this is you should definitely have one state of charge estimator for each current sensor. So if you have multiple parallel strings, then it would make sense to perhaps run multiple Coulomb counters because you have different current sensors. But then in terms of voltage sensing, it's really down to where that voltage is being sensed and whether you've got access to that information. I think one of the problems is, especially for large grid storage systems, you might have tens of thousands of cells in the system, and it's not really practical to get all of the individual voltage measurements and pass them up to the BMS or EMS. So I think there's still a gap for research and development to demonstrate that doing stuff on a very detailed cell level for a large scale system is actually going to make a difference. And I'd be interested again in your views on that. But it looks like this audience at least thinks that cell level is where you want to go.
So David, you want me to change to the last question? Okay.
Yeah, I just wanted to pause for a second to see if anyone had comments on this.
Okay.
I mean, so Michelle says, do we even have multiple parallel strings in electric car battery packs? Yeah, that's a good point. So I think my experience is no, not in an EV. You probably just have a single string of cells in series or cell bricks in series. But in a grid system, you can have parallel strings. So you might have, in a grid system, you might have modules which are connected in series, and then the top and bottom end of the string of modules is connected in parallel to another string of modules. So obviously this presents some issues with balancing and some problems, but yeah, it becomes much more complicated to solve this issue with large batteries. Samar says, for recycling batteries, which one becomes important? I don't know, Samar, do you want to elaborate on that? I'm not sure. Could we unmute Samar maybe, Pablo? I think we have a bit more time. What do you mean exactly by that? If it doesn't work, don't worry.
Yeah.
I guess what you might be saying is which of these measurements or which of these estimations is worth doing for recycling and second life, maybe. Yeah, and yeah, sorry, do you want to tell us?
Yes, hi, sorry. Yes, I had this question that, because for recycling batteries, the estimation of lifetime is very important because it's the trend right now that batteries can be used for a second lifetime in another purpose. So I was wondering, in order to use batteries for the second lifetime, which one of these, for example, cell, pack, or module becomes important?
Yeah, that's a very good question. And I think it will depend on the cost benefit of deconstructing systems for second life. The systems I've seen, for example, with a company like EcoStore, I think they just take the entire pack from a Nissan Leaf, for example, and reuse the pack. So they don't necessarily pull out individual cells, but I guess if you could make it cost effective to remove individual cells, then you could do cell level second life. But my gut feeling is at the moment, it's too expensive to do that. So people are looking at modular pack level second life, in which case you kind of tend to reuse the BMS that already came with the system in the first place. But maybe that's throwing away some value. I don't know. Okay, shall we go to the last question then?
Yes, we have 5 minutes, so it's okay.
Great. Yeah, okay, so this one I would love to hear your views on. So what are the most important remaining issues, basically open research questions for battery control? And you could choose from demonstration of improvements in performance and life, so this is like the validation question, parameterization, characterization techniques, model order reduction, dealing with new chemistries, or others. And again, if you think others, then I'd love to hear what you've put for others. Yeah, so at the moment, it looks like, maybe I can say, it looks like we've got a pretty good idea of what the tools and techniques and opportunities are, but what seems to be lacking is demonstrating that it can make a real difference in the real world and make a real impact. So I think there's probably definitely some room for projects and experiments which show the impact. But then coming in just behind that is this area of parameterization and characterization techniques, which we already discussed earlier. So I guess it's not surprising that these map quite nicely onto the pain points that we discussed at the beginning, where parameterization and validation came out as key pain points. And then model order reduction, dealing with new chemistries, seems to be a little bit less important. I would be interested in why people think that. Perhaps it's because lithium-ion is becoming the dominant chemistry, or perhaps it's because actually a lot of these control techniques can be swapped out and applied to a different chemistry fairly easily. In that case, thanks very much for joining this breakout room. I hope it was useful and interesting. If you have further thoughts, comments, please feel free to email me or get in touch with the De facto project. My email address, just to remind everyone, I can put it in the chat. It's david.howie@eng.ox.ac.uk.